times that we want. Oh, should I restart my talk or should I just continue? I just heard that recording started.
No, we can.
I think just proceed.
I just proceed? Okay.
Just proceed.
All right, good. And the third is the period length delta. So we've seen a talk in the same setting, or almost the same setting in the morning sessions, and I'm gonna later on explain a little bit more the differences between the settings here. So we make a few simplifying assumptions. So in this problem, we want to place, we want to schedule each connection or each edge once per period. And also we assume that the connections are bidirectional or undirected, and that the traversal time is 1, which corresponds to the strict setting as where we want that paths or temporal paths use strictly increasing time labels. And our task is to find a label for each edge such that afterwards the travel times for each vertex per U and V is at most what the matrix prescribed. And this is the crucial difference to previous work, where often that was required to be the exact travel time. And here we treat it as an upper bound. And to be a little bit more formal, so what does, like, how's the travel time defined? So these labels that we've tried to find for the edges, they define a periodic temporal graph where each edge appears basically at this time modulo delta. So if I select time TE for HE, it appears at time TE, T plus delta, T plus 2 delta, and so on and so forth. And the travel time, which I will use small delta UV from U to V, is the duration of a fastest path from U to V in this periodic temporal graph. Yes, and I have a little example to illustrate this a little bit. So as a reminder, the duration of the fastest path is the first label minus the last label, sorry, or the arrival time minus the first label of the starting time. And for technical reasons, we add a +1 to reflect this traversal time of 1. And when I say label here, I mean the actual label that is used by the path, not this representative modulo delta that we picked. So if I have a small example graph here, and let's say this is at least a part of my distance matrix. So for 5 vertices, this is already pretty big, so I didn't want to give a full example here. So the distance matrix prescribes that if we want to go from A to C, we should use at most 3 time units. So if I place label 1 on the edge AB, I can place label 3 on the edge BC. I could also place label 2. And then from A to D, we want to use at most 6 time labels. So this is the actual travel time that I achieved. So I can put label 2 here. So if I go now from A to B and then from B to C, the actual label I'm going to use is 2 plus 4, the next larger one that is available, so 6. And then I will have the actual travel time also 6. Now, if I go back from D to A, then I use 2, 3, and then 5. So the next larger label here. And this will give a travel time of only 4. But since we are in the upper bound setting, this is fine. And last but not least, here, if I want to go from B to E, and I want to use 3 time units, then this needs to be label 1. So 1 plus 4 is 5. So this will have traversal time 3. And here we can see if I use the same requirement on the reverse direction, I can actually force this to be 3 and 1 or 2 time labels that have difference 2, more generally speaking. So just to give you a little bit of an intuition of this problem. And what are our results? So this problem is difficult to solve. So this NP hard, even if the tree has a constant diameter and also the period length delta is constant. And it also is NP-hard if the tree has constant maximum degree and the period delta is a constant. On the positive side, we could show that this is fixed parameter tractable with respect to the number of leaves of the tree, which is also sometimes called the max leaf number, which is also a parameter for general graphs. But here in the special case for trees, it's equivalent to the number of leaves of the tree. And in the second half of the talk, I want to talk a little bit about how this fixed parameter tractability result is achieved. But before we do that, let's compare a little bit these results to previous work. So there's previous work on temporal graph realization with exact distances. There are actually two previous works that both appeared at Sand this year. So, by the way, this is not the paper title. I just wanted to illustrate what these papers are about. So here, the problem, we require the distances to be exact, but we don't restrict the graph to be a tree. And this is NP-hard even if delta is a constant. It's W1 hard with respect to the feedback vertex number of the graph, but it's FPT with the feedback edge number of the graph. So in particular, we can solve this problem here with exact distances in polynomial time if the input structure is a tree, which we cannot do if we have upper bounds. So this is a significant difference between those two problems. And then there's a second work about which we heard a talk earlier this morning, where on top of requiring exact distances and allowing general graphs as the underlying topology, we also can place multiple labels per period on each edge. And here some of the results are that this is NP-hard on stars, even if the number of labels that I can place on each edge is a constant. It's fixed parameter tractable with respect to the vertices of the graph and also with the vertex comma number combined with delta. And there are some further results in this work that are not so easy to state without introducing extra terminology. So we can see that requiring upper bounds instead of exact distances seems to change the problem quite dramatically. And now for the remainder of the talk, I want to show you a little bit how we achieve this fixed parameter tractability result here with the number of leaves. So the general idea is that we reduce the problem to mixed integer linear programming. So I'm sure most of you know what this means, but let me briefly tell you what MILPs are. So essentially, we have a set of variables, and some of these variables are considered integer variables and some fractional variables. This is where the mixed comes from. And then we have a constraint matrix and two vectors B and C. And if you want to consider this a decision problem, also some target value T. And we ask ourselves whether there's an assignment to the variables such that all integer variables are actually set to integer values. We obey all the constraints encoded by the constraint matrix. And we also want to use non-negative values. And we want that the objective function that we want to maximize is at least the target value T. And this problem here is known since the 80s by the famous result of Lenstra to be fixed parameter tractable with respect to the number of integer variables. So if we can keep the number of integer variables small, we can have a large number of fractional variables and we can still solve these fairly efficiently. And we are going to use one particular technique, which I think might also be interesting in other contexts if you have not seen this before. So we use that if we can design the constraint matrix for the fractional variables, so that basically means that I treat all integer variables as constants. And if the remaining constraint matrix is totally unimodular, then the MILP admits an optimal solution where all variables are set to integer values, not only the integer variables. And I don't want to define what that means because we are going to use later some sufficient condition for totally unimodularity and not prove this explicitly. But you might know this also from the context of linear programming. If you have a linear program and your constraint matrix is totally unimodular, then this linear program admits an optimal solution with integer values. So this is clearly a generalization because a linear program is just an MILP that doesn't contain any integer variables. Okay, so now to design this MILP, we need to talk about travel delays, which is a basically a formalization of how long agents wait at vertices if they travel along fastest temporal paths. So if I look at the vertex V and I have two neighbors U and W, and let T U V and T VW denote the two labels on those two edges, then the travel delay when I go from U via V to W at W is defined as follows. So if this is the larger label, if the second label is the larger one, then we just subtract the two labels, and otherwise we know that we will actually not use that label, but one delta period later, so we have to add delta to it. And this essentially just quantifies how long we are waiting at this intermediate vertex V. And we can rewrite the duration of a fastest path also as the sum of travel delays plus one. Again, the plus one, because we want to consider the traversal time of one here. And so what I also just want to note is that if we know all the travel delays, we can recompute the labels at least up to a constant, because obviously you can add a constant to all labels and this will not change any travel delays. So why is this useful? We want to use those travel delays as the variables of our MILP, right? Because we can just create a variable for each travel delay, and then we can add a constraint for each vertex pair that checks that the actual duration, which we just saw we can express through the travel delays, is at most the duration prescribed by the matrix. And but there's one problem with this that we need to solve. Because if we have a high degree vertex, to which I will refer to as high degree vertices, I will call vertices that have a degree larger than 2, then we can run into the following problem. So let's assume we have these travel delays, and also let's assume that they are all integer. And here I have a travel delay of 1 from A to B. So if I label AV with 1, then I have to label this with 2 to obtain this travel delay. Now I could also have a travel delay AC from A to C of 1 via V, so I also have to label this at 2. And now you can already see that if now I want that the travel delay from B to C is 1, then this doesn't work, because here the travel delay of delta is 3 is actually 3. So these set of travel delays are not realizable. So if I just have these variables and these constraints, I have to make sure that the travel delays are actually also realizable. And if the vertices have degree 2, this is not a problem. But if they have degree larger than 2, I have to somehow enforce this with additional constraints. But thankfully, this situation cannot happen too often, because if a tree has L leaves, then we can observe the following, that first of all, the maximum degree of the tree is also at most L, meaning all the high degree vertices have degree at most L. And also the number of vertices with degree larger than 2 is at most L. So the situations in which we have to add these additional constraints is the number of situations is bounded in our parameters. So we can introduce additional integer variables to try to deal with this. And this is essentially what we're going to do. So to be a little bit more formal, we create a fractional variable xVAB as a travel delay from A to B at vertex V. And we assume that the vertices are ordered in some arbitrary but fixed way. And then the first vertex here is always the first one in the ordering, and the second one, the second one. And of course, we only create this if A and B are actually neighbors of V. And what we now do to deal with the high degree vertices, we create an integer variable for each label that is then of an edge that is incident with a high degree vertex. So note that the number of integer variables here is bounded in the parameter, because we know that the number of high degree vertices and also the degree of those vertices is bounded by the number of leaves of our parameter. And now what we can do is for each high degree vertex, we can guess the ordering of the relative ordering of the labels incident with that vertex. Now this allows us to, if we want to compute the travel delays, to know which of the label is the larger one and whether we need to add delta to the second label or not. And these integer variables we can use to ensure that the travel delays of the high degree vertices are realizable. So in particular, this means we can just let the ILP, the MILP, make guesses for the labels, and those labels will then, with equality constraints, essentially directly give us the travel delays at the high degree vertices. And now we can just put the duration constraints as we briefly discussed earlier. So for each vertex pair, we just add up the travel delays along the path from S to T. And now we can distinguish 4 different types of travel delays. So the first row here are the degree 2 vertices. And if we traverse them forward, meaning from A to B, then we just take the travel delay. If we traverse them backward from B to A, then the travel delay in the opposite direction is exactly delta minus the original travel delay. And here in the second row, we do the same thing for the high degree vertices. And then we check that this is at most the prescribed duration. But we know essentially that the second part here, we know that those values are going to be set to integer values because of the constraints we introduce to deal with the travel delays at high degree vertices. So basically, the duration constraint, if we treat all the integer values all the integer variables as constants, it simplifies to something like that. So here I just added this C on the other side, which should be the travel delays at the high degree vertices, and what remains is the travel delays at degree 2 vertices that we traverse in a forward manner and in a backward manner. And now what I claim is that this is essentially what remains as the constraint matrix for the fractional variables, right? And what I claim is that these constraints form a so-called network matrix, and network matrices are known to be totally unimodular, which means there's always an optimal solution where also these values here are set to integer, these variables are set to integer values. And informally speaking, the requirement of a matrix being a network matrix is as follows. So every constraint corresponds to a path on some directed tree, and the variables correspond to the arcs on that path. And if an arc appears forward, then the coefficient should be 1. And if the arc appears backward, then the coefficient should be -1. And here you can already see that this is somewhat, we have this structure. So if this is traversed in a forward manner, we have coefficient 1. If this is traversed backward, we have coefficient -1, because obviously all these deltas we can also push to the other side of this inequality. And to close this out a little bit more formally, how do we construct this directed tree to formally prove that what we constructed is actually a network matrix? So assume this is the tree that is part of our input tree. So it's a little bit cluttered, but I essentially just numbered the vertices and the edges. And I assume that this numbering of the vertices is also the ordering that I'm using to create those variables. And what I can do is I can take the line graph of this tree, which has a vertex for each edge here, and two vertices are incident if the edges share a common endpoint. And what I can do now is the cliques of size at least 3 in this line graph correspond to the high degree vertices in my original tree. So what I do is I merge these to a single vertex, and the remaining edges I direct in the way the middle vertice, the vertices corresponding to these edges are traversed. So this yields this directed tree here. So we merged all of these to this middle vertex, and now this arc here corresponds to this vertex V2, which was corresponding to this edge, and it's directed upward because the neighbors V1, V3 are ordered in this direction, and the same with the two other arcs here. And this is now a directed tree, and whenever we want to traverse, or we have a path in this original tree, there's a corresponding path in this directed tree that's essentially skipping over the high degree vertices, and the arcs here essentially correspond exactly to the D3 two vertices for which we want to add up the travel delays. And if these arcs are traversed backward, then we will traverse the corresponding vertex here in the backward direction, meaning we consider delta minus that travel delay. So this essentially shows that these constraints here form a network matrix, which means that the whole constraint matrix for the fractional variables is totally unimodular, which means that there's always an optimal solution where all variables are set to integer values. And also note, I didn't mention this before, we don't have an objective function here because we just want to find a feasible solution to this mixed integer linear program. And we know that all the durations are obeyed, and then from the travel delays, we can start to reconstruct the labels. So to wrap this up, so what we did in this work is we looked at the new temporal graph realization settings. So the big difference here is that we require that some upper bounds are obeyed, and we observed some surprising differences in the computational setting complexity compared to the setting with the exact distances. And on a more technical level, we used an MILP, and we designed it in a way that basically guarantees that there's always an optimal solution where all variables are set to integer solutions. And I think that that technique or that trick, let's say, can also be useful in many other contexts. And for future work, so on the one hand, of course, also in this setting, it would be interesting to generalize, especially the algorithmic results, to multiple labels. And it also would be interesting to see whether there are some non-tree-like topologies that we can still get algorithmic results for. And more generally speaking, this area of temporal graph realization is still, I would say, fairly unexplored, and there are probably a lot of other natural settings that are waiting for you to investigate them. So that was all. Here's a link to the manuscript that the talk was based on, and thank you.
Thank you, Hendrik.
So are there any questions from the online audience first? I think you can just unmute yourself and speak if you have a question. If not, then any questions from the people in the room? George?
So I'm still thinking about it, so I'm not sure if my question makes sense. Have you looked at approximations? No, I'm not sure what approximation here means. Maybe you're given some times on the distance matrix and you're allowed to go a constant factor away from them, generate your solution, something like that. Have you thought about it? Have you looked at it?
Yeah, so we have not looked at it. I'm not sure others have looked at this. I'm not aware of anything, but yeah, the main issue here is exactly what you mentioned. If you want to do approximation, you have to define carefully what it is that you actually want to approximate. And yeah, like one possibility is that the distance matrix gives you kind of target values that you can either overshoot or undershoot, but you kind of want to reach them as good as possible. Or maybe you can only undershoot them. You are not allowed to go above. And yeah, then you could try to find a solution that is as good as possible. Note that in our case, we do not care how much we undershoot those values, right? So we could have durations in the labeled graph that we produce that could be much, much smaller than what the matrix says. So I think in some sense, the approximation setting is even more natural in the setting where we have exact distances that we try to achieve. Or we could, in this setting, we could also approximate the number of entries in the matrix that we are able to satisfy, in the sense that our duration is actually smaller than what the matrix gives us. But yeah, so generally, I think this is a wide open field with a lot of interesting questions that can be explored. But we have so far no results in that direction.
Thank you.
Okay, any other questions from online or in the room? If not, I have one more question. So you assume that the tree is given to you as part of the input.
Yes.
What if I just give you the distance matrix and I say I want a tree with edge labels that realizes that? Do you think I'm not to your techniques, or have you thought about this variant of the problem where you can select the tree you want to use?
No. So first of all, we haven't thought about this, and I'm also not aware anybody else looked at this particular setting. Yeah, so I'm thinking whether our hardness results work. I mean,
if I say I want a tree with at most L leaves, but then just enumerating all possible trees would be too much, I guess, right? So it's not obvious how you would solve it.
It is not obvious, yeah. Yeah. Yeah, that's so there's a
there's a comment from you.
Yeah, one entry still force the underlying tree.
If you have one entries, they could force a tree, but you could also have inputs where all values are greater than one, and then you don't know what tree you would want to use.
Yes, yeah, but this should imply that the hardness results all hold.
The hardness results will definitely.
Yeah, right. But yeah.
Okay, then let's thank Hendrik again.